Okay, part 3 of 4 here. So let's move on to energy. So more specifically, kinetic energy. So our old version of kinetic energy looked like this. Kinetic energy is equal to 1/2 times the mass of an object times its velocity squared. And it was measured in joules. Our new version of kinetic energy, you could probably guess this by now because of the way things get substituted. It is 1/2 times everywhere there used to be mass in our physics now gets replaced by rotational inertia, and everywhere there used to be velocity gets replaced with rotational velocity. So rotational kinetic energy is 1/2 times the rotational inertia times the angular velocity squared, also measured in joules. There's no equation to go between the two because we normally add the two together here. So a common thing they might do is something like this, where you have two objects rolling down a ramp. And one thing they might ask you is who gets to the bottom first? Well, let's say we have a disc here, like a solid disc. Like imagine you sawed off a little circular piece of a log, and then you have a hoop where almost all the mass is on the outside here. So the hoop has a much bigger rotational inertia than the disc. Why? Well, remember what rotational inertia is. Rotational inertia is, if I can actually, all right, here it is. It's the mass times the radius squared. So all the mass over here has a bigger radius. Some of the mass here is in close to the point of rotation, so it has a very small radius. So everything out here is all the way out at the edge, so it has a bigger radius and therefore a bigger rotational inertia. Therefore, the hoop is harder to get rotating than the disc. And if you let them go at the same time, then the disc would get down to the bottom first because of that. So one thing that is important again is we must have friction. Just like we mentioned in the previous one, if we don't have friction, then both of these actually would get to the bottom at the same time. They would just slide down. And that would be kind of like often rather than a disc and a hoop, they may compare either one to just a box on a ramp with no friction at all. In that case, this one is going to get to the ground in the fastest amount of time because it doesn't have to rotate at all in order to get down to the bottom. So these guys are not only resisting accelerating down the ramp like this guy, but they're resisting rotating down the ramp, and therefore it's harder for them to get moving there. So that's a common question that they might ask. Another way they could talk about it in terms of energy, they may make you make an argument on it based upon dynamics. And so in that case here, these guys, if you say, why does the disk get there sooner? Well, if acceleration, angular acceleration, is the torque over the rotational inertia, it's got a smaller rotational inertia, therefore it will have a bigger angular acceleration. So you could make the argument with dynamics. So let's go back to this for a second and look at what's going on with the energies here. So in the old-fashioned way, when we have the ramp, or the box going down the ramp, then we have got gravitational potential energy is going into just old school kinetic energy, this kind, what we might call linear or translational kinetic energy. But when we go down a hill and we are rotating, like with the disc and the hoop, then our gravitational potential energy is not only going into linear kinetic energy or translational kinetic energy, it's going into rotational kinetic energy. So since some of the energy is now bound up in rotating, then that means there's less energy available to move to the side. So both the disc and the hoop must be going not only will they take longer to get to the bottom, but they will be going a slower speed when they get to the bottom because of that as well. Again, this guy, whatever gravity, assuming all these are the same mass and all these are the same heights here, this guy, the mass cancels out in the energy equation, so actually the mass doesn't matter. But this guy will have all its energy in linear, and these guys will have some of their energy bound up in rotational. And then the last thing we want to point out with this is, again, another way you could look at these is with energy. This one has a bigger rotational inertia. So that means it's going to have a bigger chunk of its energy bound up in rotational energy, which means it's going to have less energy left over for linear. So the hoop will get to the bottom last, and it will also be going slower, therefore, when it gets to the bottom.